So with that, yeah, again, welcome to my session and the talk today about distributed systems. I'm going to give a little overview of different approaches, how distributed systems, or in a more modern form like microservices, can be implemented. Now, before I start and going a bit more into that, just some quick words about myself. I work at a company called Novatech as a cloud native consultant, so to say. This is probably where some people might know me from. What a lot of people probably don't know is that I also work as a teacher or lecturer at 2 universities in the area around Stuttgart, where I kind of teach distributed systems. And yeah, distributed systems is a bit of an old and gray kind of terminology. So what I try to do is kind of distributed systems with modern technologies. There are quite a few out there. And yeah, if you want to reach out to me, LinkedIn, Twitter, many other things will work, but this is probably where you can find me best. Also, I will probably not be around all the time for this conference, unfortunately, because I'm kind of currently teaching a class, so I sneaked out in the lunch break to give this talk. But if you want to get in contact with me, this would be good options to start. Now, I said distributed systems with modern technologies. So these are modern technologies, the way I consider it at least. And these are things we are going to look into this talk today. I should probably say that the initial version of this talk I created for the lovely Spring I/O conference in Barcelona. So it has a pretty stronger Spring flavor. But over time, I tried to add some other aspects of Java in general, Micronaut and Quarkus. I mean, Spring Boot is probably the framework I'm most familiar with, but the concepts and the things that I try to explain today really apply for other frameworks too. So this is not something which is kind of limited to Spring Boot or Spring Cloud only. All right, so before we're gonna start comparing different approaches of implementing distributed systems patterns, I first want to start with a why. Why would people actually go into a distributed architecture? What is the things and how would you do that? What you need for that? And then based on that assumptions, or hopefully common understanding here, I want to compare that along the different options that you have, and also try to help you figure out which would be the best thing for you in your situation to apply. Do you actually need it at all? So I mean, just because there are microservices and Kubernetes and things like that doesn't always mean this is the solution for everything. So I hope this will get you a bit of an insight of when and what to apply when those tasks might be given. So I think I have roughly 15 minutes, or 50 minutes, they're gonna cut me off. In case if you have any questions on the way, feel free to add them to the chat. I'm not so much of a fan of putting all the questions towards the end. I mean, sometimes things might have to be explained right on spot, and I'm definitely happy to do so. In case if the question doesn't really fit in, or if it will be answered later throughout the talk, I will just let you know then. So yeah, don't be shy. I'm happy to answer in case I really know it. All right, so looking at a distributed system or a distributed environment, in most cases, kind of maybe a microservice environment as we see it nowadays. Or let's say in general, if you build software, no matter if it's distributed or not, you most likely build the software for a certain type of clients. I mean, sometimes you might write software for yourself, but that's probably not the most common business case. So from a perspective of the client, no matter if it's a distributed or non-distributed system, it should appear as one system where you get one UI or one API. And the idea is, of course, to shield the complexity from your clients. Now, the question will then be, what reasons might trigger you to split down one system into many? And does this make sense? In which cases does it make sense? And so on. Of course, you can see right here what you're definitely gonna get as an additional price is the network connectivity and the network thing that you have to handle in case of such a system. which might something you should take under consideration. Now, one of the reasons why people go in the direction is, of course, like one of the common cases, like the heterogeneous factor. You might even have different tasks that might be able to be executed, sometimes even in parallel, on different environments. Another heterogeneous factor is like that you might want to run on different operating system stacks, that you might have mainframes, Linux, Windows, Linux, whatever machines. And altogether, they assemble a certain system which brings a certain functionality to your client. If you go a little higher in the abstraction, this might, of course, also mean you might have just like different components and frameworks, which you cannot like really place all on one application server, but they might be individual pieces that will, in the end, form your from your overall application. So containers have been a good thing to achieve that. To give them like a common kind of interface to run on the outside, but still be able to have individual and polyglot components on the inside. And even if it's not only like different components, even if it's just like different versions in your frameworks or applications, that still might lead you to the conclusion that you run them as individual processes that have to connect to each other. A certain factor is also, of course, the ability to grow. So if your application or your system is something which is about to be extended, you might not want to rebuild and repackage and redeploy the core component all over every time. So you might want to put some functionality in certain dedicated components and allow room for further growth. So all of these aspects are under the kind of umbrella of heterogeneous components. Now, the other big factor about distributed systems is the thing about resilience of or robustness of your overall architecture. So people might want to scale up systems in order to have failovers, and in case of outages, still some standby systems that could take over. I mean, as I said, in the end, the client's going to judge how good your system is. And if they never notice if a certain service goes down, it's probably better for you. Like this kind of redundancy very often comes with factor of load balancing, that you say, well, if my users increase or my requests increase, I want to be able to serve them all. And then if you can load balance your traffic across multiple instances of your service, this might certainly help. Another factor goes in the opposite direction, to say if your users get too many, they might risk that they eventually take your system down. So in that case, it might also be a good thing to have mechanisms for blocking traffic and say, well, I might need that time for my application to recover, or I might need that time for some new instances to spin up. In that case, there will be a kind of an outage, but this is like a controlled outage, which is probably not as bad as if your systems are certainly going to crash and will have a hard time to recover. An advanced format of that is rate limiting, to say, well, I want to serve as many as possible, but I don't want to crash my application. So I'm going to throttle the traffic and only allow a certain amount of requests to get through, so my application would actually remain healthy. Security is an aspect where you can say, well, I want some certain component that checks if only certain requests are allowed or not allowed. And this is basically most of the things when it comes up to scaling your applications and allowing different routes or paths to get to it. Another factor, which is a very common case, is that you don't want to shut down your application in case of updates. So you want to provide dynamic updates. In other ways, like roll out a new version while the current version is still running, and then switch the traffic on the fly. So one thing to do this is called a blue-green deployment, where you basically just like reroute your traffic to the new instance once it's there. And an advanced form of that is like a canary deployment, where I say, I'm only going to let dedicated traffic to the new instance. This might be a percentage thing. This might be like a cookie-based thing, where I say, or like a request-based thing, where they only requests from a certain geography will get to that. That's like what big companies do very often. In the end, you kind of want to have a gradual upgrade from your old version to the new one, and not like just a hot swap. So I guess there are probably more, but these are like the most common cases that I have seen so far why people would say a distributed system might make sense. Now, what do you need to have in order to get there? I mean, this is one is, of course, like a no-brainer. It's pretty obvious. They have to communicate, and that also means they have to speak the same language or protocol. Another very important component, or a component I'm probably going to talk a lot in this talk, is like I don't know how to call it, network routing, traffic shaping component that can be placed in various layers of your stack, and which also have different options to like either route, distribute, throttle, or even block the traffic to basically fulfill those things that we have seen in the initial steps. Another thing which is very important, especially if your landscape grows large, is kind of a telephone book. So a service registry where each service that joins will basically say, hello, I'm there, and you can find me under this telephone number, and then services can do a lookup and find it. Distribution means also distribute a configuration. So if you have many things flying around and you want to update certain configuration aspects, you might have to do that all at once for a certain amount of things. So that needs a certain mechanism to distribute configurations to many instances. And finally, not only configuration, but also retrieve information in form of metrics, logs, traces, whatsoever, to figure out, are all my applications doing fine? And if something is not all right, you basically might want to correlate that to do a meaningful error analysis. So all in all, it's quite a bit that you need to do to get your distributed architecture set up properly. And this is something you need to be aware of if you want to go in that way. Otherwise, it might just not be the right choice. So this is like a sample infrastructure architecture that I kind of sketched here with like where you have 4 services, 2 backends, then a kind of API gateway in the front, and all of those services also being connected to service registry, distributed configuration, observability. So you can see even on a small scale of like just 4 components, this can get quite complex, and it's not going to decrease a lot once you grow any further. But then, of course, you're going to get those possibilities that we were kind of dreaming of in the beginning, to say, yeah, I want to scale applications, I want to load balance between the scaled instances, I want to roll out new versions while other ones are running, and so on. So I have a pretty dynamic and flexible infrastructure. And this is basically something I will try to compare now to say, well, how can you do this with like frameworks of your application language? How can you do that with something like a runtime or a platform like Kubernetes, and things on top like service meshes and eBPF? So one thing that should probably be mentioned here is Netflix, because I mean, Netflix was obviously one of those companies that had a very distributed and scaled landscape. So back in those days, when they became popular and had that need, there were not like Docker, Kubernetes, and things like Cloud Foundry were not such a big thing yet. And so they realized they have to implement all that behavior with own frameworks or like own libraries. Fortunately for us, they provided all these libraries in a Netflix open source kind of stack, and people could use it and for their own purposes too. So you will see that like this component I've talked about before, you will get in many different aspects here. So in terms of like a circuit breaker, you have blocking or throttling mechanisms. In case of load balancing, you have distribution. And in case like of API gateway, you have like routing and making sure that traffic goes where you want it to go. So and that also already shows a bit of this framework approach, where you basically as a developer will place exactly that functionality that you need to have right in the component where you need it, and only there. So this one became somewhat more popular with the adoption of Spring Cloud, that basically partially reused that libraries, either extended it or wrote new ones or added different ones. So this is basically time when I got familiar with this technology, maybe 2016, 17. And for most of you, some of those names will probably still be familiar, like Eureka as a service registry, then configuration server. methods for resilience with either Hystrix in the beginning or later on resilience for J, ribbon and feign for load balancing and declarative clients, and so on. So you see that library is kind of extended in order to provide additional distributed applications possibilities, so to say, to your application. The way those work internally, and this is an example here from Eureka now, but this will probably be similar to many others, is like you have a mixture of like a dependency, like either Maven or Gradle, of course, that way you add your dependency as a starter, and then you have an annotation or some code reference where you enable that. So that means to activate those functionalities, you basically need to go on a code level. This is the counterpart where you basically enable discovery client and then make sure you can use Eureka as a telephone book, basically register yourself and or look up others. In that case, again, you have dependencies, code, and sometimes also configuration properties to get there. A final sample is here for the Spring Cloud Gateway, where you can do like routing and a lot of other functionalities. But again, the nature of things is that you add a dependency and add some configuration or changes in the code, which will basically give you this functionality. Now, the good thing about this approach, of course, is you can take dedicated components and say, I want this functionality here and I want this functionality there. And then it doesn't matter if those components run as an own process on one machine, like in the example here, or if they run as a process all on different machines or different VMs, or also what has, of course, become very popular to run in containers. If you add it to your application server, not application server, but your application level, it's basically it makes it independent of the underlying runtime, which is, of course, a very important feature. Now, I said I want to talk a bit about Micronaut and Quarkus as well. Well, I need to admit I don't have as much experience with those as I do have with the Spring Boot framework. But I mean, a lot of things are relatable and similar. So Micronaut doesn't really come up with an own implementation of libraries and functionalities to address those challenges. So on the one hand, it of course allows using starters to integrate with the Netflix libraries, but you can also use, for example, console as a service registry or configuration source, or then resilience for J. So they basically adopt to an existing ecosystem and make it pretty easy to integrate those components to, in the end, achieve the same functionality. With Quarkus, there's a bit of a different approach. They also have, they include a set of libraries from SmallRye, which is kind of a set of APIs and implementations, which I think initially comes from MicroProfile, but then is also adapted from Wildfly and OpenLiberty. So these are also a shared set of Java libraries that you can use to achieve those things like health checks, service discovery, fault tolerance, and so on. So to sum it all up, with all three kind of Java enterprise library or like libraries, so to say, you can do all those things without the need of an underlying runtime to cover that. So the characteristics here again is like you make the changes on an application level. So you need to rebuild and reboot your service in case you want to make that change. But in the advantage that you get, it's then completely independent of the framework where it runs, and you can apply it everywhere. So you're not dependent on a Docker or Kubernetes or whatever. This brings you a lot of flexibility there. Also, it's fairly lightweight because you can basically say, well, I only need the load balancing here, and I only need the back pressure or circuit breaker here. And for the other components, I'm just not going to add it, and I'm not going to waste additional overhead to put them in just in a standardized way. Now, there is one thing to consider, like when, as I said before, when Netflix and Spring Cloud became popular, this was a time prior to the, let's say, hype cycle of Kubernetes. And so in that case, you can clearly see the libraries had more responsibilities to cover that. Now, with Micronaut and Quarkus especially, they already, I think, had Kubernetes, or maybe like an implementation like OpenShift in their mind, which they could rely on. So a lot of those functionality wasn't essential to be built in, because this is something you could take from the underlying framework. Now, looking into Kubernetes, I'm not sure how familiar you are with this technology. I certainly don't have the time to explain all that here, but in general, you can imagine it like looking back at this picture where you run all the workloads in a container. Kubernetes is like a distributed container runtime that allows you to run the containers across nodes, and makes this architecture more like extensible and scalable that way. One thing to know here is Kubernetes has like a smallest unit, which is called a pod, which is like an additional abstraction layer around the container. But from a high-level perspective here, you can just say it's similar of us as running containers in a distributed world. Now, the thing with Kubernetes is Kubernetes was already born with that idea that you would want to run distributed applications and distributed architectures on that infrastructure. So it came up with own artifacts to facilitate exactly those requirements that we had seen before. So it comes with an own service registry. It comes with own means for configuration, for external configuration. It has built-in support for updating the versions, scaling, and distributing the load. So as one sample, there's, for example, the Kubernetes service object, which fulfills two things at the same time. So first of all, it registers itself in the service registry of the cluster. So after that, the service can be found and invoked by others. And it also does some kind of load balancing across all instances of a given pod. So this already takes, of course, some functionality away that you would normally put in by using libraries. It also has the concept or for using external configuration, and of course many more. So I'm not going to go through all of them. So that of course means, so what are you going to do if you already have an architecture which is based on the libraries being included, and now suddenly you run it on Kubernetes and the implementation come out of the box. So in the end, it's your choice. I mean, Spring Cloud has a bit adapted to that. So if you had used Eureka in the past and you wanted to switch to Kubernetes, then they have an almost equivalent starter for Kubernetes to basically use the Kubernetes service registry instead of the Eureka registry, but you only had to exchange dependencies. From a code and configuration perspective, it stayed almost the same, so you didn't really have the need to change very much. Of course, it doesn't really make a lot of sense to run Eureka in a Kubernetes cluster because there is already a service registry given. For config maps, it's a similar thing. You can adopt config maps in Spring Cloud, and then you use them either as Kubernetes objects, or you can access them via code by using that starter dependency. So to sum it all up, at this point, Kubernetes takes a total different approach. I mean, Kubernetes is totally agnostic of when it comes what is going to run inside of my containers. I mean, technically, this doesn't all need to be Spring Boot or Quarkus or whatsoever. Kubernetes only runs the container, and then whatever is in the container will be executed. So Kubernetes tries to provide those functionalities from the outside. So the routing and the config components in the service registry, they're not part of the applications anymore. They are part of the underlying platform. Of course, this has the advantage that this suddenly works now with all kinds of application frameworks. So no matter if it's Rust or Go or Ruby whatsoever, or still Java, it will work in the same way like for the other ones. However, it also means you pay the price all the time, even if you need it or not, because those things are going to be built in. It's probably, well, it's basically on par when it comes to scaling, load balancing, service registry. but it's not equivalent in terms of resilience patterns. So configurable routing or blocking traffic or being basically traffic aware is not something that comes out of the box with Kubernetes. And we're going to see in a second how that can be addressed. Now, finally, looking at Spring Cloud. So if you have started with Spring Cloud and you want to go towards Kubernetes, it's not such a big deal. I mean, you have two options. You can leave it the way it is and ignore the Kubernetes facilities, but you can also adapt to them and just change the dependency to Spring Cloud Kubernetes. But technically, if you haven't started with it yet, you don't really need it anymore because Kubernetes will provide that. All right, so let me look at the time. So this looks okay. Now, as we've seen, we have two different approaches with frameworks or platform. However, the platform has a bit of shortcomings to basically implement all of the functionality that you can get through the frameworks. So service mesh was an initial idea to cope with that. So for those who haven't worked with service meshes yet, I'm going to give just a brief introduction. So as I said before, Kubernetes runs the workload in pods. So it runs the container in pods. A pod is basically a construct where you can have more than one container. So it will be bound to the Kubernetes network traffic, and you can potentially put multiple containers in there. While this might not make a lot of sense for application containers, it might make sense for other things, because what you need to know is if you have multiple containers in a pod, they will automatically share the same network. They don't need any additional configuration. Or to say it in another way, one container will always see what the other container sees. And that, of course, gives room to say, well, maybe I'm going to use that for like a proxy or an agent-like feature. So I'm going to leave the application as application container, but I'm just going to add some proxy component, which will automatically get all the network traffic which the application gets. This starts to make a lot more sense if you don't just add it into one pod, but into pretty much every pod, because then you get a pretty good grip of what is like my network behavior all across my cluster. So you see inbound, outbound traffic, and you not only see it, you can actually also control it. So there are terms like a data plane, which is the part within Kubernetes where the data is being collected or being like actions are being applied. And there's also the control plane where everything is being aggregated. And this is where it can be visualized. This is where it can be also automated or like taken actions upon the observed information. Now, again, this, as it is in Kubernetes, doesn't really care so much what is running in the container. It's actually not caring about that at all. So that gives you the possibility to say, well, I can use all kinds of application frameworks or programming languages. This is happening not even on a container level, this is happening on a pod layer. So I'm injecting this proxy container into every pod, and then it will get the network traffic from each of my application components. Also, what it makes pretty helpful here, that your actually application pod probably won't even notice. So you don't have to rebuild your container or restart that or whatsoever. They're just going to stay the same. So it's just going to be added and will then basically start to work and collect the information. Now, if you look at our sample again, and in this case, I would just say, well, basically what will happen, the pod's going to be extended and all the proxies will go in there, and they will basically go in everywhere, not into like just a single deployment, but into each and every scaled pod. This is basically the advantage and the disadvantage at the same time. I mean, you get your observability information right from the source, but you have to place the agent everywhere. And if you start like connecting, and you basically need to connect this to this control plane, where you can see it suddenly can get messy. So sometimes people refer to it as a service mess as opposed to service mesh, which is of course a very unfair thing, but you can see where this is basically coming from. Now, in the end, you can get some functionality out of that, which you otherwise just would not have. As you have control over each and every component, you cannot deliberately say, I want to like secure or like isolate this network traffic so that only those components can talk to each other, because you control the network traffic here and there. And you can do that by using the Kubernetes API and create objects that will then be applied and being used. So this one basically makes a query depending on the source labels and say only like traffic from that source is being able to route the traffic to that destination. Another thing, so this is not only like the encryption, you can also block the traffic or throttle the traffic or do like security encryption between them. A lot of possibilities are there. So another thing is also the traffic split. So you can say, I have a new version and I want to roll out only 25% of the new version. Then you can give that destinations a certain weight, and then those things are going to be applied in that way. That also makes it very easy to change that on the fly. So you can increase or decrease the percentage whenever you feel like doing that without the need to basically interfere with your application container. So there's more. These are all the things that you can do with it. You can actually go as far as to use that for resilience engineering and fault inject deliberately in certain components and see how the overall architecture like copes with that. But if you look at all of those things, you will probably see fairly soon that these things are very similar, that what you can do with like an application gateway or like a proxy component. Now, that's because technically it's a very similar thing. Just the difference is, in this case, you have one gateway at like the entry point of your application, and here you have that in every pod injected. So if you find yourself building more than one kind of these proxy components, then you maybe the service mesh would be an idea for you. In the end, of course, a very nice side effect is the observability that you get, because you suddenly can easily see, well, how is the flow of my application traffic? Where is something encrypted? What is the rate? What is the percentage? And so on. And you can also do then like versioning things and see how the distribution of the traffic happens and so on. So especially for people new to the technology or just getting started with it, this is can be a very helpful visual representation of what's kind of going on in your cluster. Now, this is a more sophisticated example. This is actually the Spring Pet Clinic, as instrumented by Istio. So you can clearly see where is my traffic going and flowing, and of course, you can also interfere with it then and say, well, I want to route this one there, I want to block this one, and so on, and apply all those things with Kubernetes API tasks. So while this sounds, of course, absolutely great, this, of course, comes with a price. There has been a benchmark in 2021 comparing the different, like the two major service mesh implementations, Linkerd and Istio, to just see what kind of additional overhead would they generate. I mean, by the nature of things, of course, it's pretty clear that you have an additional network hop for each and every call in every service. But it's not just that. Of course, you have like this proxy component in every pod, which has an own footprint in terms of CPU and memory. So this is something you certainly need to be aware that this is a price you're going to have to pay when you adopt that. And of course, also, it's an additional layer of components you need to manage. So yeah, I try to not be super advertising on the various technologies, because each of them has a certain kind of functionality scope, but each of them also has a bit of a price. Now, in summary, those service meshes are like language agnostic, and you can extend the Kubernetes for the limitation of this traffic awareness and traffic shaping. The concept is you put a sidecar, as it is called, or like a proxy container into every pod. And yeah, you get everything straight out of the box. In turn, you're running in a pod, you're not running in a container. So if you want to go into like deeper level, like tracing, you're not going to get any application level metrics. You only get the level, the metrics on the level of the network, because that's basically where it listens. Again, the configurations change at runtime, not at compile time. So you don't need to modify anything on your existing application. All right, so I think I have maybe 10 minutes left or so. That's should actually be okay. I haven't seen any questions yet, so I hope you are all still with me. Now, one of the technologies you probably hear quite more frequently in the last couple of weeks or months is a technology called eBPF. And people might want to think, how does this fit into the picture here? If you look at the name of it, this stands for Extended Berkeley. Sorry, this was too quick. Extended Berkeley Packet Filter. This again doesn't really sound very much like a tooling that you might apply for distributed applications. To have a look where it is coming from, and I'm kind of hoping I'm not getting any deep dive questions on this, because frankly, I would just not know. But I can try to explain it the way I understood it. Technically, this is a functionality which is very deep in the Linux kernel. So it tries to interact with the network behavior of the Linux kernel on the lowest level. So normally you cannot execute any kind of custom code in the kernel space. Basically, you run your code in the user space. But with eBPF, you have that functionality to run. Oh, sorry, is there a question?
Yeah, we have a question there in the chat. Maybe you'll have a look in the chat.
It's about the graph. Okay, let me go back to this. Thanks, I got it.
Sorry, I was a bit late with the question. Apologies.
No, I mean, you're referring to this diagram right here.
Yes, yeah, my question was, so, I mean, the latency baseline versus mesh looks reasonable until the 90th.
Okay.
Like there's a big jump in particularly for Istio from the 90th to the 99th. Like the difference between the baseline and the mesh is massive from the 90th to the 99th. Do we know why? I mean, this is a very detailed thing, but.
No, I mean, I can say that quickly. I don't know exactly why. And I mean, this is why I put the link there, where you can read that benchmark in detail. I mean, I don't really want to go into the discussion of how much overhead you're actually going to have with a service mesh or not, because they're pretty configurable. And it also depends quite a lot of like how your application works, like what kind of is your request rate, how many distributed components you have, and so on. So I don't really want to nail them down and say, well, this is the exact amount that you're going to get. The only thing which I want to make obvious and clear is that there is a certain overhead, and it can definitely affect the overall traffic in your cluster in a way that you would notice that. And this is something what a lot of people will not see in the beginning. So they look at, hey, I need Kubernetes, I need service mesh. They set all that up and wonder why suddenly their application is so slow. Very often with applications that wouldn't even need it. So yeah, this is just, yeah, I should probably know more about that chart once I put it in. But to be honest, I don't. It's really just to show there is something that you should expect. And do your tests and evaluation if this is really something you are willing to pay for.
Thank you.
I hope this, I know it's not a satisfying answer to your question, but as I said, again, this is not really my point that I want to make here. I mean, what is the exact amount that you will pay? It's just like there will be something. I mean, this is for sure. And also maybe putting this into context with eBPF in a second, you will see the point that I'm trying to make. Now, going back to eBPF, in a simple way to explain it, this is at least the explanation that I was given, is like you can run sample, like your own code in a sandbox environment of the Linux kernel in a similar way as you would run like JavaScript code in a web page. So it can do functionality there, but it's basically not able to be any harmful, or at least it should not be, towards the kernel itself. And if it runs there, it can then kind of like grab kernel events, and network events are kernel events. So you basically, as opposed to listen on a network close to a pod, you can now listen right within the kernel on certain events, and then forward this into the user space where it can be processed any further. Now, how does this relate to what we're going to do in Kubernetes? In Kubernetes, I said before, it's like a distributed container daemon. So it runs on a couple of nodes, and those worker nodes normally happen to be Linux nodes. So that technically means this eBPF functionality will be applicable there as well. So you can, in general, the node will host your container daemon, the Kubernetes objects, and then run the containers. So if you run that eBPF right there, it will, of course, also get the entire network flows of the isolated container instances. And looking back at the overall picture of Kubernetes, then you can have a similar concept of control plane and data plane as you had with service meshes before. Just in this case, you have your proxy or edge component not on a pod level, but on a node level. So most likely, you will have a lot more pods than nodes. So the overhead that you're going to get is you only pay that by the amount of nodes. And then looking at this picture again, to visualize it, as opposed to putting those things into the pods, you would run them right on the nodes and then collect your information and metrics and send them to the control plane from right there. That also means you won't affect the running pods in Kubernetes at all. So you don't even have to add and change something or add a sidecar container. Your deployments and pods are totally going to be untouched. And the entire configuration takes place on a node level of your Kubernetes cluster. And then there are some toolings around. One is, it's called Cilium, where you can also then apply certain network policies, where you can say, yeah, doing similar things like we've seen with Istio before, match traffic by the labels of certain pods, and then say, okay, I'm going to only allow from this source label to this target port, or whatever you feel like setting up as a network policy. Now, I've mentioned this Cilium technology. This is like an open source technology, but there's also a premium and paid version. They are doing quite a bit in that space at the moment. So they're fairly young, and so they're just building a kind of a service mesh over time, driven by the requests of their users. So they did a bit of a survey, I think, end of last year or beginning of this year, to see what kind of functionality would users want to have from a service mesh. And we see things that we've seen before, like rate limiting, circuit breaking, retries, routing, A/B testing, and all that. But to a big surprise, observability was actually the #1 feature that was what people said, at least in that survey, they want to have as a functionality from your service mesh. So this is the first thing they kind of rolled out. They brought up a UI, which is called the Hubble UI. And this is like the same underlying application where I used the Spring Pet Clinic. And it was pretty impressive because without any changes, you would suddenly get all the network flows and see who is talking to whom over which ports and so on. So again, this helps quite a bit in understanding. And on top of that, they're going to roll out, of course, additional features. I'm not sure where they are currently at. I mean, I'm not working with this every day. But as you can see, they're already doing some network policies there. I think the mutual TLS encryption is something which you can use there already. And this is just growing over time. At this point, I think I have to wrap up things a little bit. So yeah, the technology change here is really that you have a lot of less amount of proxies that you need to inject because you put them into a different level. That, of course, means this is also something that you have to be allowed to do in your Kubernetes environment. But then you can leverage this functionality, which is actually coming from low-level Linux for Kubernetes. And this is still very young. So, I mean, I think I have heard about this first time 1.5 or 2 years ago when it was brought up at the KubeCon with a technology called Pixie back then. And I tried to play around with it ever since. And so far, it's not on an equivalent level that you can do the same things as with traditional service meshes. But I think if it works out that way and the things that it promises, that can definitely mean a change in the service mesh behavior, or potentially a future without pod-based service meshes and rather like node-based ones, because like the performance which has been measured so far is definitely a lot better and has lower latency than as you have to inject it in every kind of pod, which is of course quite natural. In the end, to sum things up, I mean, you have seen different options now for all the things you want to do around distributed systems. You can place it into your application processes. That makes you totally independent of everything else. You can rely on a platform. That means you need that platform, you're dependent on that platform, but in turn, it frees up your application from those dependencies. Or on top of that, you can use service meshes with either sidecars or eBPF. I mean, none of them will give an answer, at least I cannot give it, if your application really needs that. This is something that you need to decide for yourself. The only thing I of course, wanted to highlight today, that these options are there. They're basically free, and it's not really hard to try them out and play with them. So this is kind of my recommendation, of course, to make you aware of those things and recommend you to play with it. Also, of course, sometimes mixtures might make sense. I mean, of course, it's no point to using redundant features like a service registry in Kubernetes and Eureka. But like having, for example, as we see here, an eBPF-based thing, and then still using a Spring Cloud config server is, of course, a viable configuration because they don't really overlap in their terms of functionality. All right. So first of all, I would like to say thanks for listening, and I can see quite a few people joined, so I appreciate that a lot. I hope I was able to tell you something new at least, and didn't waste your time that you could have otherwise spent for an extended lunch break. As I said, I will probably check the messages that I get in the JCON, like logged into JCON, but I will be probably busy this afternoon and tomorrow for teaching a Kubernetes class. But yeah, if you want to get in contact, feel free to ping me on LinkedIn, Twitter, or I think I'm probably on other networks as well, but these are the ones I'm going to use mostly. So with that, I would open up this for more questions, but I'm at the end kind of a thing, and I can't see anything right now. All right, so I can see a few compliments. Of course, I happily take those as well. And yeah, feel free to spread this if you have, like if I will make the materials available online, and the recordings will be there in a while too. So yeah, thanks for being there, and I wish you a beautiful lunch break.